We've been talking about how functions and sets relate to each other and how we can use functions to talk about how big certain sets are. Today, and moving forward for the next week or two, we're still going to be talking about sets, but we are moving away from talking about infinite sets, and we're focusing on finite cases. Today and next week, we're talking about counting techniques, which sounds like the topic for a kindergarten class, but obviously we're not learning 1, 2, 3, 4, etc. We're learning or discussing some techniques that we use to count something more efficiently. What do I mean by that? Well, let's say that you're standing in the middle of a big sports stadium, and your goal was to count how many seats there are. Well, we wouldn't actually go through and count each one individually. Maybe we look at a certain section and we say, oh, there are a certain number of rows, and each row has a certain number of seats. So we can multiply these things, and we get the number of seats in that section. Maybe then we multiply by the number of sections we see, and we count the number of seats in a stadium by doing something else. Right. Right. First thing today is to make a few ideas that we inherently know a little bit more formal. So if we have two finite sets, so we're focusing on finite sets today, if we have two finite sets A and B that are disjoint, so this line, or disjoint, means that there is no overlap between A and B. There's no elements that are in both A and B. Right. That's an important piece. But if we have two sets that are disjoint, then the union, or the size of the union of the two sets, is just the size of the sets added to each other. Right? So let's take a look at an example of this. If we have our set A is 1, 2, and B is ABC, then the set A union B is the set 1, 2, ABC. So in other words, the size of A union B is the number of elements in the set is just 5, which is the sum of the number of elements in A plus the number of elements in B. Right. This is contrasting this Cartesian product, A times B. So things in this set look like ordered pairs where the first element is something in A and the second element is something in B. So A cross B is the set of ordered pairs that have that property. So 1A is one of the elements in this set, as are each of the other combinations of 1, 2 with ABC. That's what the Cartesian product is. So we can see that the size of this set is the size of A times the size of B. And we can imagine that this works for any finite sets A and B. Well, this idea seems reasonably straightforward. The size of the union of sets is the size of the sets added together. The size of a Cartesian product is the sizes multiplied together. One place where the usage of these rules can get tricky is when it's not inherently obvious what type of set it is that we're talking about. So a habit that I want us to get into is taking some word problem and identifying what the component sets are and identifying which of these rules or what type of counting technique we are using in terms of these components. Let's take a look at another example. So say that a restaurant has 6 appetizers on its menu and 8 main courses. So one question we can ask is, how many items are on the menu in total? And this is not meant to be a trick question. So if there are 6 appetizers and 8 main courses, then in total there are 14 items on the menu. So I want to walk through a couple of implicit assumptions that we made when we answered 14 to this question. The main one is that we assume that there's no overlap between these two sets. If A is the set of appetizers and M is the set of main courses, then, well, in order for this logic to hold, we need A intersect M to be empty. Right. So this is a question that we can just do in our head, but a way of notationally keeping track of what's going on, if again we call A the set of appetizers, then the size of A, the magnitude or the cardinality of A, is equal to 6, while the cardinality of M is 8. Since we have the property that the intersection of A and M is the empty sets, then we can apply our first rule, our addition rule, saying that the union of these two sets, which is the collection of all the items in the menu, is the sum of the size of the two pieces, is 6 plus 8. I would say that the trickiest part of this question is recognizing that the question is asking for the size of the union of the sets. Right. For part B, how many different combinations of one app and one main can we possibly have? Well, this is a question about the size of the Cartesian product of these two sets. In other words, elements in this set, possible answers to this, as in combinations of an appetizer and a main, consists of ordered pairs with one appetizer and one main. How many total options do we have? Well, for each appetizer, we have 8 mains to choose from, and there are 6 appetizers. Therefore, the total number of combinations of one of each is 6 times 8, or 48. This is another question that we don't have to use sets to answer, but especially when we start doing more complicated questions, using this notation, keeping track of what we're calling a particular set, so writing down something like, let A be the set of appetizers, then we can give this a framework and have a sort of a consistent terminology with which to tackle these problems. So again, I would say that the most difficult part of this, or the trickiest part, is recognizing that what we're after here is the size of a set, or the size of the Cartesian product of these two sets. All right, there was an important assumption that we made early on. In order to invoke this rule, that the size of the union of two sets is the sum of the two sizes, we really need the two sets to be disjoint. If there's overlap, then weird things happen. All right, so how do we deal with that? What do we do if the intersection is non-empty? In other words, if we have our two sets, A and B, if there is some overlap, well, how does our counting technique deal with that? All right, we're going to start off with an example. Let's say that A is just the set AB, and B is the set BCD. All right, I'm sure we can notice that the size of A, or the cardinality of A, is 2, while the cardinality of B is 3. So what is the cardinality of the union of A and B? Well, this one we can just answer by listing out the things that are in A union B. That's going to be A, B, C, D. And we can see that, hey, there are 4 things in this. Notice that 4 is not the same thing as 2 plus 3, which was the equation we used in the previous question. So what's changed in this example? Yeah. Well, there's an element B that's in both of these sets. If I said that the union contained 5 elements, it contains this one, this one, this one, this one, and this one, well, then we're double counting the elements that are in the intersection of A and B. All right, so how can we adapt our formula to remove this problem of double counting? Well, we can take the number of elements in our first set and, again, add them to the elements in our second set, and then just subtract off the amount of double counting that we've done. So we're going to subtract the number of elements in the intersection of A and B. All right, so this is the inclusion-exclusion principle. The idea is that the size of the union is the size of each of the pieces adjusted for the amount of double counting that we have. Right. I personally really like Venn diagrams, so the explanation for this using Venn diagrams is as follows. If we want the union of these, well, we could take A and we could take B and we could add them together. So let's move this piece over, but you'll notice that if we line it up right, the overlap is darker than it should be, right? These are transparent components, and because the overlap is darker, that's meaning that, hey, we're counting it the first time and we're also counting it the second time. So to adjust for that, if we had this piece, this circle plus this circle, minus the overlap, then if we put those things together, we're left with the thing we actually want. Another way of seeing this is that if we first do this last part, if we take a circle and we subtract off this overlap, the thing that we get left with is this crescent moon-like shape. This shape plus this other shape is equal to the total piece in question. I think of the inclusion-exclusion principle less as a formula and more of an idea, more of a consideration that we need to think about when we are talking about sizes of sets. So this idea can be generalized to questions that involve more sets. So if we have 3 sets, and we want to know how many elements are in the union of each of these 3 sets, A union B union C, what we're after is how many things are in this whole picture. Well, to figure that out, we can add up the elements in A, B, and C. However, we're going to start double counting some regions in this, much as we did with the 2-set example. So one issue that we're going to have is that this region is double counted by A and B. Well, maybe we should subtract off that piece. Well, this may cause some issues down the road, like how does this relate to this piece? I'm leaving the details of this question for you to work out in your groups on Friday. Obviously, feel free to think about this question between now and Friday, but if you do solve it, be sure to give the rest of your group mates time to think about it and to discuss it in class on Friday. Don't just jump in with the answer. Yeah. All right, so we are just gearing up with our counting techniques. Next week, we're going to be talking about combinations and permutations. These are ways of counting different, combinations that we can make from a larger set. And we'll be extrapolating on some of these ideas that we covered today. One of the main reasons that we want to talk about combinatorics, or methods of counting, is that this can be used for probability questions. So we can answer questions about the likelihood of something occurring if we can count the number of ways that it can occur. More on that probably 2 weeks from now.